Now let's consider a set builder form of a set which we identify whether the two set builder forms are equal sets or not equal sets. The previous examples were taken in the roster form, so now let's attempt identifying the equal sets for a set builder form, taken with the following example. So my first set L is considered to be X such that X is a letter of the word assassination. So the word considered here is assassination, and my set builder form of the first set is that X such that X is a letter of the word assassination. Now my next set, say I take M, is X such that X is a letter of the word station. Now there are two different words taken in case of the two different sets L and M in set builder form. Now I want to convert them into the roster form and then identify whether the two sets are equal or not equal sets. So to start with, I want to convert the first set L into the set builder form. So going by the definition which says that X such that X is a letter of the word assassination. Now the roster form, as we have taken in the previous sessions, we identified that the letters are not repeated as one of the rule. Therefore we take all letters provided they are not repeated again. So when I take this, A is the first word, S is the next word, then S, A all taken again, so not repeated. A and S are not repeated. And the next letter I identify is I, and then I identify A, and then I identify T, and then I identify O, and the rest are all repeated. So the letters I identify in the word assassination are A, S, I, N, T, and O. Similarly, when I convert the set M into the set builder form, equally using the letters of the word station, I start with S, fine, next T, and the next A. T has already come in, so I don't consider. Then it is I, and this is O, and this is N, are the words I take from station. Now I wanted to identify whether the two sets are equal. Going by the definition of equal sets, the two sets A and B are equal if A is subset of B and B is subset of A. Therefore, the sets L and M are equal if L is subset of M or M is subset of L. And I use the cancellation process to identify the equal sets. A gets cancelled. S with S, I with I, N with N, T with T, O with O. So clearly I identify that all the elements of the set S are cancelled with the elements of set M. Therefore, L is subset of M. Similarly, all the elements of set M are cancelled with the elements of set L. Therefore, equally, M is subset of L in the reverse process. Now, when A is subset of B and B is subset of A, immediately something shoots in mind, that is A equal to B. Therefore, L subset of M and M subset of L implies L is equal to M. They are equal sets. The sets L and M given in the set builder form are equal sets, is how I understand the equality of sets in mathematics. Now let's take one example which is quite interesting to understand the equality of sets or even the subset concept using this peculiar example. So for example, I take any set A is equal to, with my own example, as 3, 5, 7, 9. Now my set A is consisting of 4 elements, 3, 5, 7, 9. And I don't have any other set given out here. Then my question out here for you all is the set equal to itself? The question is, if A is equal to this, then is the set A equal to itself is the biggest question in this example. So how do we prove mathematically that whether the given set is equal to itself or not? So initially I take that if my set A must be equal to A, then A should be subset of A or A subset of A and vice versa. So therefore I understand that if I take the set A as 3, 5, 7, 9, then I reconsider the set A equally in the second case because I use the cancellation process to identify whether the set is equal to itself. Now this clearly makes me understand that every element gets cancelled and obviously A must be subset of A, and reverse way also this is subset of E. That implies A is equal to A strictly by the definition as we considered. Therefore every set is equal to itself. Is equal to itself. So it is very important to note that when you take a set, it is equal to itself because it is the set itself. Is how we understand in general form, but mathematically we prove that a set is equal to itself by using strictly with the equality definition. Also, there's one important note which comes out here in the form of A is subset of A. So you take any two sets which are same, reconsider the set A, then obviously A will be subset of A. Also makes me understand that from this property I understand that every set is subset of itself. A very important property in mathematics. Every set is subset of itself using the property out here. Every set is equal to itself and every set is subset of itself is how I understand the properties when I consider the set alone. So now that we have come to the end of the session of sets, the last topic which we want to discuss in this is about Venn diagrams, which ends the topic of sets. Now Venn diagrams are very important because we cannot write the sets randomly all the time. So Venn diagrams help us in minimizing the situation, the complex, however complex situation the given problem might be in. So we have to learn how to write the Venn diagrammatic form of the various sets as given in the problem. So what is the Venn diagram? It is a very simple definition. The diagram which is used to denote the sets is a Venn diagram. The most simple definition is it. The diagram which represents the sets. So Venn diagram is the diagram which represents the sets is how I understand. As we already discussed in the previous session that the universal set is usually denoted with a rectangle. So we always have a rectangle drawn first in the Venn diagrams because a rectangle stands for universal set and every Venn diagram starts with the universal set, that is a rectangle in its diagrammatic form and denoted by mu. Now whatever sets I give inside, say for example I give a set A, then I say this is the Venn diagrammatic representation of the set A under the universal set mu. So this is called Venn diagrammatic representation of set A under the universal set mu. So there are many examples where I may not consider only one set. There will be more than one set, around 2 to 3 sets, which I have to take at once in drawing the Venn diagram for the given problem. So before we start with the in-depth concept of understanding the Venn diagrams, let's try to understand the basic operations of sets. The numbers have their operations which we do with plus, minus, multiplication and division. Similarly, Venn diagrams or the sets have 4 basic operations which we're going to discuss in the continued session. To start with, union of sets. The first operation in sets is the union. So let's see what the union operation is and understand the definition and the diagrammatic form for understanding all the 4 operations continued with. So there are basic operations of sets which we're going to discuss in this session. Just like the 2 numbers are added, then addition is the operation when they're subtracted, minus is the operation when they're multiplied, multiplication is the operation, and when we divide, the division is the operation. Similarly, 2 sets are also with few basic operations. The 3 basic operations which we're going to discuss in case of our syllabus is union. This is of course for the sets, and the next is intersection, and the third is the difference. The fourth is the complement, which is indirectly related to the difference. So the basic operations of sets are identified to be the union of sets, the intersection of sets, and the difference of sets. To start with, union of sets, initially with. So what is union of sets? The word union means uniting the 2 sets. I want to unite the 2 different classes. I want to unite the grade 10 section A and grade 10 section B. So when I want to unite or make the union of class 10 section A and class 10 section B, then I call all the students of 10A and 10B, I put them together in one class. It's called union of 10A and 10B. Similarly, when I have 2 sets A and B, I take all the elements of set A and all the elements of set B, then all the elements together of A and B, just like all the students together of section 10A and 10B, will form the union of the 2 sets A and B. The union of 2 class sections 10A and 10B. Similarly, the union of 2 sets A and B is how I understand the unity or the union of sets as compared to the real life situations. So let's start with the basic definition. So union is the combination, is the combining of sets. That is, indirectly when I say combining of sets, I mean combining of all the elements of individual sets. When I say I'm combining 2 classes, indirectly I mean combining all the students of the class. Same way, when I say I'm combining 2 sets, indirectly means I'm combining all the elements of set A and set B, say for example. So union is the combining of sets, that is elements of the sets considered. Let's understand this more clearly, but before that, I am very particular about the notation. So how do we denote the union is the biggest question out here when it comes to the terms of notation. Union is denoted by U. U stands for union and the symbol stands for union. That means A union B implies, I can write mathematically as this, which makes me understand that this U is directly related to union. So therefore, A union B implies A union B is how I understand the union notation. So let's see with this with an example problem. So when it comes to the example, let me take a set A 1, 3, 5, 7, 9, and my set B is 0, 1, minus 11 and 7. So for these two sets, I would like to take the union. Therefore, my A union B, which is denoted as union, is understood with combining all the elements of set A and set B. To start with, I write all the elements of set A, which are 1, 3, 5, 7, 9, and I write all the elements of set B. If it is repeated, I write only once, because if the student is in both the sections doing the common course, then I don't try to include him 2 times, but he's included as one common student in the combined class. Similarly, when 2 elements are repeated in both the sets, I write as one common element. Therefore, when I have 1 which is also there in this, I repeat only once. So already written, I don't write it again. Then comes minus 11. Similarly, 7 also is repeated here, so I do not write. So the repeated elements are taken only as only once. Therefore, my combined elements of A and B is 1, 3, 5, 7, 9 and negative 11. Therefore, this is the union of 2 sets, is how I understand the concept of union. The union of 2 sets A and B is this, with its respective definition. Now let's see the Venn diagrammatic representation of union. How do I represent the union in a Venn diagram is also very important, because when I understand the concept of sets, I understand the sets both through the algebraic approach and also through the Venn diagrammatic approach. So let's see the Venn diagrammatic approach of union of 2 sets. Now, if I take the same example as I considered in the previous session of the set A and B, and I found the union, let's try to draw the Venn diagrammatic representation for this, because the same example would stand as understanding of the Venn diagrammatic representation for the union of sets. Therefore, when I take the set A and set B, my union which I got through the algebraic approach is 1, 3, 5, 7, 9 and minus 11, which when I want to draw through the Venn diagrammatic representation, I initially start with the universal set A and the set B. Now, because there are some common elements between 1 and 7, I just take this in the form A and B with some part which is co-joined with this other set B. Now, if I draw the sets A and B, now comes what is A union B. Now, because when we take 2 sets, the combination of 2 sets is union. Therefore, this entire region stands as union, as I understand through the definition. So this is union of 2 sets. This is union of 2 sets, is how I understand the union. Now, what comes inside A and B? So union of 2 sets is the shaded region here, denoted with the shaded region. This is A union B, and the elements here are 1, 3, 5, 7, 9 and minus 11, but because 1 and 7 are common, I have 1 and 7 in this common region, because this is both in A and B. 1 is in A and 1 is in B. Therefore, when I draw this, 1 is inside the circle A and 1 is also inside the circle B. Similarly, 7 is inside the circle A and also in B. So this is the region where we write the common elements. That is the first rule in Venn diagrammatic representation. The second rule in Venn diagrammatic representation. So 1 is inside A and 7 is inside B, equally both sharing. Next, the remaining elements 3, 5, 9 are in set A. Therefore, I write 3, 5, 9 in the set A, and then the remaining elements 0 and minus 11 are written in set B. This is how I understand the union in Venn diagrammatic representation, with this being the universal set and this being the set A and set B, with all the elements filled in the shaded region A union B. So A union B in Venn diagrammatic representation is this, and the algebraic representation is this.